Hi everyone, my presentation is a stability comparison of two autonomous vehicle platooning algorithm using 2020 built-in module and the spring mass damper system. In this presentation, we're gonna have introduction and problem identification. Afterwards, we're gonna go to actually introduce SMD and Vissim built-in platooning modules. We would have simulation scenarios and simulation results. Finally, we're gonna have conclusions and recommendations. Well, taking advantage of platooning autonomous vehicles can potentially double the roadway capacity. It also could increase safety by avoiding human errors. That's why this title is taking lots of attention from researchers. Several models for AV platooning are proposed and tested either in physical testbeds or traffic simulation softwares. We're gonna introduce few real-world pilot programs for AVs. On the left side, you can see NYC autonomous shuttle, which is in service since August 2019. This shuttle is servicing in private roadways in Brooklyn area, New York. On the right side, you can see autonomous impact protection vehicle, which is in service since August 2017 in Colorado. Moreover, the US DOT have developed 10 test beds in 9 different states. So it's an opportunity for researchers to have a chance to test their models, their autonomous vehicle related models in real world circumstances. The problem is that still there is not a unified platooning system for autonomous vehicles. And platooning algorithms could be at risk of a spacing error in case of unstable conditions, such as a speed change. A spacing error, actually a positive spacing error could cause in maximum capacity drop, and a negative spacing error could be a safety threat, which should be avoided. The spring mass damper model actually has a long history in physics, but the model which we started from was developed in 2017. This model is based on basic physics rules. Each vehicle in this model is considered as a mass which is connected to other vehicles by a spring and damper. A spring constant and damper coefficient. A spring constant defines sensitivity to a speed deviation between two vehicles, and damper coefficient defines the sensitivity to a spacing error between two vehicles. In this model, acceleration rate of each vehicle is updated in each time interval. In a way, finally, they maintain the desired distance, which is function of speed. In this SMD platooning model, spring constant and damper coefficient are function of flow. So in case of very low flow, there would be no tendency for platoon formation. And in case of high flow, there would be actually a very long platoon of several vehicles, which we believe is not desirable in real world circumstances. So we made some adjustments on existing SMD model. First of all, we set limitations on maximum communication range to make it more compatible with real world conditions. Second, we actually deployed constant values for damper coefficient and spring constant to reduce the platooning time. And thirdly, we set limitation on maximum number of vehicles in each platoon to actually be welcoming to potential merging vehicles. We coded the algorithm in Python and shooted it to Vissim software by COM interface. So as you can see in this slide, there is a video of our simulation run. We have several type of vehicles in this video. The blue vehicles are human-driven vehicles which won't join the platoons. The orange vehicles are leading platoon vehicles which are in communication range with other vehicles. Green vehicles are following platooning vehicles. and yellow vehicles are leading platooning vehicles which are not in communication range with the vehicles in their front. On the other hand, we have Vissim 2020 built-in platooning module, which has several adjustable parameters. In a parameter setting for Vissim 2020 built-in, we try to set parameters in a way to be compatible and comparable with our SMD model. So we set maximum number of vehicles in each platoon to 4, platooning following up gap for 0.5, and minimum clearance distance to 2 meters. And we also have the same parameters in SMD model. And the safety distance has the same formula in Vissim 2020 module, which is a function of vehicle's speed. We selected 3 scenarios with potential of a speed change to evaluate those 2 platooning algorithms. First one is variable speed limit, second one is following an aggressive human-driven vehicle, and third one is lane closure, which would cause a queue formation, a crawling phase, and queue discharge. In this slide, we can see simulation results for variable speed limit. In variable speed limit scenario, the speed drops from 100 km per hour to 60 km per hour. An error of 4.5 meters is observed in Vissim built-in module at the end of a speed transition phase, and it takes 11 seconds of moving with constant speed of 60 km per hour for this error to be faded. But for SMD model, no noticeable error is considered in this scenario, is observed in this scenario. The second scenario was following an aggressive driver vehicle. In this scenario, a human-driven vehicle suddenly decelerates from and reduce its speed from 100 km per hour to 30 km per hour. And afterwards, our platoon has to follow that human-driven vehicle with that constant speed of 30 km per hour, which is less than or platooning desired speed. In this scenario, maximum error of 10 meters is observed in Vissim built-in platooning module, which actually, after 40 seconds of moving with the constant speed of 30 km per hour, the error drops to 2.6 meters. On the other hand, for SMD model, we don't notice that peak of error. We observed increasing error, which actually finally would go to 2.6 meters, exactly the same as Vissim built-in module, and never goes less than 2.6 meters. So in both models, we have a constant error of around 2.6 meters if they are following a human-driven vehicle with a speed of 30 km per hour. The third scenario is queue formation and queue discharge, which is followed by lane closure. In this scenario, actually the vehicles are moving with a speed of 100 km per hour. Then they face a queue. They have to actually shift to a standstill or crawling phase. An error of 30 meters is observed in Vissim built-in module at the beginning of a standstill or crawling phase. While the vehicle starts to crawling or standstill, the standstill condition, the error drops to 7 meters, but never goes less than 7 meters in Vissim built-in module. Afterwards, when the queue starts to discharge, it takes 18 seconds for the error to be fully faded. On the other hand, for SMD model, we observed an error of around 1.5 meters at the beginning of queue discharge phase. Well, a negative error is not observed in any of the models, which means both could be deployed without safety concerns. Regarding the positive error, positive errors are observed in Vissim built-in module, which could cause in capacity drop, but such error is not observed in SMD model. Potential future studies could be deployment of SMD platooning algorithm combined with other models to provide an uninterrupted flow at merging sections or ultimately at intersections. And actually finding optimum number of vehicles in each platoon, considering platooning vehicles with different characteristics such as mass or acceleration deceleration rate and processing time, adding lane changing logic to the platooning model could be considered. Thank you for your attention. I can answer your questions.
Thank you, Artie. We do have some questions.
Right.
The first one, is recovery time equivalent to the string stability?
Yes, the time it takes for the string to become stable, to have the desired distance. Yeah.
All right.
It's the time which takes for the error to be completely faded.
Awesome. Thank you. The next question, what is the maximum number of platooned vehicles where the error increases up to the point that the stability is not reached?
Maximum number of vehicles in each platoon, right? Actually, we set limitations on maximum number of vehicles in each platoon. We set 4 here in both models, in Vissim built-in and in SMD model. I couldn't understand second part of your question. Could you please say it again?
Yeah, so where the error increases up to the point that stability is not reached.
In which scenario?
No, it's what will be, I think that the question goes that what will be your guess that there is a maximum number of platoon vehicles that up to that point, neither any model nor the one in Vissim or the one that you built will reach capacity, stability. We know that you already said that is 4 vehicles is the one that you study, but could you make any guess?
We didn't actually try any other number than 4. That's what we have to consider in our future studies. We just selected 4 as a random number.
Perfect. Yeah, and it makes sense. In fact, for vehicles like they say 4 tracks, I think that in the Coexist project they were saying that up to 3 they can assure stability, but more than 3 no. So I think that your number is a proper one.
Yeah, we didn't actually consider that changing the number, and seeing what happens. We actually mentioned that for future studies, trying with different number of vehicles, or actually number of vehicles in each platoon could be function of other variables, which we didn't. Was not goal of our study,
No, it's amazing. It's just a following up of that question. Really good. Sorry, Brandon, go ahead.
Oh, okay. Thank you, Murillo. Thank you, Artie. What is the communication range determined in your algorithm?
Yeah, actually, the communication range in our algorithm is function of speed again. Here in this slide, you can see the communication range we set in our study. Is actually 3 times bigger than the desired distance between vehicles.
Awesome, thank you. Right. And then the final question, why do you think that your results vary so much from the Vissim built-in module?
Actually, I don't know what is the logic between Vissim built-in module platooning, because in manual is not there is not lots of detail, but that's why I don't really know the reason for that. I know the SMD model very well because I coded it in, and I shooted it to Python, but I don't know how Vissim built-in module is working. I don't have lots of detail about that.
Well, there is no detail because we protect our algorithms. That's good. Well, but probably one guess on that. Do you think that it could be because of the aggressiveness inside, or something on that like? Well, what would you think that is the difference? Let's try, I guess.
Actually, I have no idea.
Okay, no, we are not going to put you in an awkward situation.
Thank you.
Okay, I did have a last minute submission here, so we'll try and squeeze this one in. Will your report in the future include details such as, sex of the driver, car model, time of driving, other effects that would, especially like aggressiveness for drivers, teenage drivers, at different age groups, that would affect the driving conditions in the model?
Actually, I'm comparing the spacing error in this study, and a spacing error is not desired. It shouldn't happen. What I'm presenting here is that in SMD model, a spacing error is not happening. I tried to model different, different circumstances which could lead in a spacing error. What we considered was variable speed limit, which is a smooth speed transition, aggressive driver vehicle, which is kind of harsh speed transition, and Q formation and discharge, which has, which is a bit different, which with both of them includes both deceleration and acceleration. What we observed finally, we actually didn't observe noticeable error in, we didn't observe a minus valued noticeable error in any of the models. But we observed the positive value errors in Vissim built-in model, which meanwhile we didn't observe, any error in SMD model. So these errors should be avoided. Even in these three scenarios, this is actually a noticeable error. This error shouldn't happen. And so what I can say is that, but I don't know why this error is happening. In Vissim built-in module. Because I have no access to the code, or I don't know about the details about the algorithm.
Thank you, Artie. All right. We can get in touch with you after this if you have more questions.
Sure.
With the software. I'm going to reintroduce Murillo. She's going to introduce our next presenter.
Thank you very much. And yeah, sure, it's a good idea. We will keep in touch just in case where the values were getting from. So thank you very much. A really great presentation.
You are very welcome.
Thank you. So now we are going to go to Hamed Esmaeeli from Concordia University in Canada. So please go ahead, Hamed.
Hello, thanks PTV team and attendance here in this poster presentation. It's a brief presentation around the evaluation of different penetration rate of automated vehicles on traffic and safety performance that I use Vissim Microsimulation as is the software here that we have. So I have a technical issue. Okay, it's passed. Okay. The major problem that we have in urban area is the traffic congestion and safety performance. And the traffic congestion in transportation networks can be seen in major metropolitan areas. And according to the U.S. National Highway, actually there is around 6 million crashes in 2018. There was actually, and 36,000 fatalities resulted in. And this is the motivation for us to go toward this direction and employ new technologies in enhancement of the road safeties that we have. So there are many solutions provided by researchers, and some propose using automated vehicles or autonomous vehicle in that phase. And the most efficient one that we target today is autonomous vehicle, because based on researchers, actually new technologies aim to significantly shifting to this area, and automated vehicles accurately detecting, identifying or predicting movement of all users in transportation. And it has a positive impact on traffic safety. In terms of using automated technology in vehicles, researchers focus on the traffic flow characteristic and the impact on the environment by using this type of technology, and there is some technology advancement for automated vehicles like ADAS or others that are out of this scope. The acceptance of people is an important issue that is correlated with the maturity of the AVs and penetration rate. So this is the target of our study, and among different levels of the automated vehicle that we have and presented by NHTSA. So the first one, it was just it has rudimentary automated functions, and yeah, it was a long time ago that they went to this area. And then in the level 1, we have actually some opportunity for traffic jam and overtaking assistant. Then in level 2, there are some cruise control and parking facilities, but these level 1 and until here actually it's out of the scope of our study, and mostly we focus on just level 3 and in some cases level 4, because in level 3 actually it's a high level of automated driving and with a limited self-driving automation, and level 4 is a full control. And there are some opportunity that we can simulate this in the microsimulation environment. Otherwise, in reality, we don't have enough data or access to evaluate these type of models and levels that we have. So the autonomous vehicle, just see if I want to just say briefly that automated technology is the best solution, as I said before, and it's a countermeasure of dynamic incidents. And there are many companies that works on the development of automated vehicles, and they propose some autonomous vehicle in actually level 3 or even 4. But a study shows that there has been a significant increase in interest in the automation of vehicles in recent years, as evidenced by advertisement and launching lower automation level by several vehicle manufacturers. And now we are close to use them, and we want to involve them as much as possible in the system. However, we don't have any other backbone for that one in the different areas, but the simulation environment can give us some view on these impacts. And the objective of this study is going to be investigating the impact of AVs in different traffic flow and reveal the influence of autonomy level for safe driving. So the core framework of the methodology that we use, sorry, is to construct scenario design. That's normal posture. Then go for the data collection, and by analyzing data, we can create the microsimulation layout. And for sure, because all default parameters are based on Karlsruhe, so it should be calibrated to be matched with the field that we have. Actually, for the case yesterday, so we do simulation calibration and then go for development of AVs in the system. At the end, for the conflict analysis and considering the road safety, we evaluated this. We use the SSIM software to evaluate results, trajectory results of the Vissim microsimulation that we have. And at the last step, we do the sensitivity analysis for all of scenarios that we develop, and we can compare them perfectly in that case. So for the scenario design, we went for having geometrical one-lane urban roadway. This is the general condition of the urban roadways, apart from highways that we have. And we have intersection approach on both sides. So we selected from the downtown of the Montreal a specific road segment that's kind of the arterial that we have here. It's really important because of the limitation of the access on surrounding roads. So most vehicles try to pass through this segment, and that is called Rue de la Montagne. And if I pronounce it correctly in French, I'm not sure. But on both sides, on both ends of the street, we have major intersections. So it makes it more real urban roadway that we have. And as you see that in the all downtown area of the Montreal, we have the grid-shaped roads, and it's a similar condition that we have here for this road. So for the transition of the AVs, that is the part of the objective of this study, we investigated on different type of AVs that we have in Vissim software. And apart from the conventional vehicle, this is the current situation that we have. We assume actually AV airborne that I will present it later, but the three others are defined with the different car following models in Vissim, and we just go to the evaluate the penetration rate of each type in the network. So the data collection that we had was from Ville de Montreal, and that we collected volumes. There was some speed data and also head rate that's extracted from the MTL target. Is database that is available under the Ville de Montreal database, and it's open data. So by extracting data of the speed, we defined actually the cumulative speed diagram of the vehicles that we have here for the speed of the 40 kilometers per hour, and that is the speed limit of that segment of the road. And we found this shape of the cumulative speed that we used later in our simulation model. So we have to implement the simulation layout. So we did it in kind of intersection. You can see that this is the schema from simulation environment. And for sure, the Vissim used the car following model. That's a Widman 74. And due to the psychophysical impact of car following model in Vissim, so it's a great opportunity that we consider it for urban area, especially in this case, as long as that we have the mixed traffic. So we have different attitude of the people, drivers for longitudinal movement. So you see that for speed, desired speed of the automated vehicle, we have the rigid one is kind of a straight line for any desired speed. For example, if it's 50 kilometers, so they all AVs push to follow this behavior, speed behavior. And then for conventional vehicles that we have, we adjusted based on the actual data that we had in the field and try to implement it exactly in Microsimulation. So the next step is to calibrate the model with the actual data. And the calibration is the process in which input parameters are already defined. So we require to calibrate the model in a realistic manner. And then in recent density, the functional various optimization algorithms on Vissim model were investigated and proposed in details optimization method. Calibrate and validate Vissim parameters, particularly for urban roadways. These are the most sensitive parameters of the car following model in Vissim, as many of you are familiar with that one. And it's for Widman 74 and used for conventional vehicles in urban area. So there are many methods we had over there. Oh, there was some problem error. Okay. We have volume-based calibration, speed-based calibration, and objective-based calibration. That prior studies focus on them, and some of them maybe use the merge of them for calibration. But here we focus on objective-based calibration, and our objective is a headway between vehicles. But when we create the objective function to make it minimize between the observed vehicle headway and the simulation one, so we need to run it for different seeds, and also we need to investigated to make this object function close to 0 as much as possible. Actually, the error should be tend to be zeros. We use different algorithm to optimize this objective function actually to evaluate it for the calibration purpose. So genetic algorithm and web optimization and particle swarm optimization are three algorithms that we use prior to this study actually on urban roadways to evaluate the condition of headway and the urban area and find this attitude of the diagram to go to zero error or maybe be constant and not zero exactly but a constant value. Apart from the length of the time, the iteration actually that we have for reaching to the zero or constant condition for each of these algorithms, we have to focus on the values that came out from each of the algorithms for these three parameters. So these three parameters should be optimized, and when the algorithm is going to be constant, gives a constant error to us. So that's the point that we have to refer to exactly these three values that we have here, and we can refer to them. And so the number of iteration is not important for us in this case. And this is the shape of the particle swarm optimization that's going to be general form. So the deviation of simulated headway distribution that I propose here, that's from the real world observed and the optimization methodology implemented in Python and connected to Vissim by using COM interface. So we did 10 random seed and 100 iteration. So the only reason that we use all these three for the test and not go further for other algorithm was the attitude of having only longitudinal movement into consideration of our simulation and also calibration that we have. So we don't have any lane changing in this way. So as a result, we found that the PSO algorithm showed the best fit for this single objective calibration that we have here. That later you can see here that the default values of the Vissim for these parameters was like these 2 to 3. The average standstill is really important if you want to actually do the safety analysis. But the calibrated values shows that yeah, the average standstill stand is similar to the default value for this by using the PSO algorithm. The additive part of safety stand is really lower, and we have different other parameters that is not sensitive for this for. But the several type of AVs that we have in Vissim algorithm, Microsimulation, defined with different type of call following model, as long as they follow the Widman 99, but they don't need to be calibrated because it's AV, and we don't have any actual data for that on calibrated. And we refer to the results of the coexist project that they evaluated by the Vissim Microsimulation for the parameter of the kind of the standard distance and other parameters that we have for the Widman 99, and use also the calibrated parameter for the conventional vehicle that we have here. There are some other factors impacted on the behavior of the AVs that, like, for example, increasing acceleration and maximum deceleration for trading vehicles. So that's the reason that we only define urban AV by higher value for increased acceleration to just see what's happened. But the benefit of using them is that AV urban has a larger gap, a higher acceleration, and use the Widman 74. So it's a kind of the assumption is not accurate because we have many uncertainties inside. AV normal consider the distance with surrounding vehicles and also can identify the speed of surrounding vehicles. AV cautious equipped with absolute braking and also follow road codes. It has a larger gap because of the safety condition that it has. And the aggressive one is the perfect perception and a smaller gap with later. It's kind of the aggressive because of the close distance that it has with the other vehicles, but it's based on the identifying the behavior of surrounding vehicles that it has. So the surrogate safety assessment method employed to evaluate the trajectory files of the Vissim. But SSM, as I said, surrogate safety assessment method is a kind of the simulation interface and facilitate measuring the number of conflicts and their severity from the trajectory file. But the higher TTC value that is defined in the SSAM and lower speed and headway variance resulting in a safer driver. But here we have an issue with SSAM that SSAM does not have a built-in function to identify conflicts by vehicle type. And we have AVs here. We cannot consider a constant maximum value for the TTC to evaluate the actually conflicts because it can give you unacceptable results. And it provides but it provides actually in the results of the SSAM the vehicle IDs within that range. So we can consider the TTC maximum be 1.5 time to collision that between two vehicles that you can see the approaches here. But we can not rely on the values, and we can use the vehicle ID and go back to Vissim and identify that is this automated vehicle, which type of automated vehicle it is, and actually distinguish them from conventional vehicle, and then go back and analyze the TTC to see is it under the range or not. So, but the purpose of having different TTC, because you know that the ABs can identify that the smaller gap. Actually, they define a smaller gap because they know each other. When they follow each other, so they have a lower gap. So in this case, the TTC normal should be deducted 1/3, and we can have 1 second instead of 1.5. It's not the exact value that we selected. We just refer to the reduction that we had in the standstill, and it's really important. So the standstill and the following distance for the calves actually were reduced to 1/3. For this season, we also reduced TTC 1/3 and we reached to the 1 second. For the cautious situation, we don't have this kind of reduction, so we keep it on 1.5 for the TTC, and for the aggressive again we have 1 second. It doesn't have impact on this case, and we consider it as a constant value of the 5 second for all of them. But as you see that for the conventional vehicles, when they follow the other conventional vehicle, or maybe when they follow the AVs, we evaluated based on TTC 1.5. And at the end, we do the sensitive analysis for the traffic flow and traffic composition and different type of AVs, and investigate on the penetration of the different level of automation. So as a result, the traffic performance that we have on the link of that urban roadway, you can see apart from the conventional vehicle that has a travel time of 77 seconds, the rest of them, when you go for the normal one, there is a reduction in travel time. Go here, and the cautious, by increasing the number of penetration of this type of vehicles, autonomous vehicle in the system, is a similar condition that we have some reduction. Yeah, it's acceptable, but actually there's no much because of the higher gap that they have between them. And the best travel time results came from aggressive autonomous vehicle. There's a very steep the diagram that shows with 100% penetration is going to be 72 seconds. The difference between this time variation that we have here for the travel time is not too much, and it's depends on the length of the street that we selected. Maybe if we'll make it longer, and and try with the other geometry of the roads, it gives us better prospect and variation. So both, all of them should be increased by the penetration of the vehicle, but the traffic performance is not the only issue that we have to consider. We need to evaluate the safety assessment. As I said, that I use the vehicle ID from the SSAM and identify the vehicle type from Vissim, and again calculate the corresponding TTC for each AVs. And by the conflict analysis, I found these results. The only CV shows that the maximum TTC that we have is okay, and there is for sure the interaction between the conventional vehicles are all included, and we have same value. But for later conditions, for the urban, yeah, I just brought the urban, but the results is not sensitive for us in this case, because we have many assumptions, but it also shows a reduction by penetration of the VC in the number of conflicts when we updated the TTC, when we used the updated TTC in conflict analysis. So we saw some reduction in these type of AVs for the conflict numbers. For the normal one, you can see the condition is not acceptable. Actually, it's going to be an increase even by reduction of that amount. But for the cautious, again, we have a reduction. But the difference, see that in the normal, the red lines, you can see that the red bars actually, and the yellow bars, if you compare them together, you can see that they have same attitude. So the updating of the TTC was not impacted on the number of conflicts here. But in the cautious, it's a different direction, and the updating of the TTC reduced number of conflicts, and it's mostly rely on the higher gap that the larger gap that they have, and the role of cautious AV. And for the aggressive condition is a similar condition. The number will be increased and it's too much. And if we compare the result with the actually travel time, you can that we did in previous slide, you can see that their normal and aggressive was good, but here maybe normal is more acceptable, and even cautious is the best for the conflicts. So the future development of the model could be evaluating of the impact of different AV preparations on the longer arterials, as I said, the geometry impacts on number of conflicts and also travel time that we have. Then we can investigate the optimal TTC, account of the sensitivity analysis of TTC time to collision for the best calibration AVs in different urban roadways, and also investigate on driver distraction in mixed traffic. That is a new facility in Vissim 2020 that we have to go more deep in that option. So thanks for your attention, and I'm here to response to your question.
Thank you, Ahmed. That was a great presentation. We have a few questions for you. The first one, how would it be to calibrate for a more complex intersection, like a roundabout? Like, how would you do that?
For the for roundabouts, it's a similar condition, but you know, we have more conflicts. We have to distinguish between the type of the movement that we have in the roundabout and the intersection. In the intersection, for example, you have many conflicts, and yeah, it's going to be regulated by the signal. So maybe the conflicts are not real, but in the roundabout, it's a real conflict. So you have to be more sensitive on the roundabout. And yeah, it's a different aspect, but I didn't go through the roundabout because we don't have it in Montreal. Maybe that's the reason. But yeah, it's really sensitive, especially for the interaction between the AVs and conventional vehicles.
Thank you. The next question, could you better explain AV urban, better define it for some people who might not know?
Urban AV urban urban AV or AV urban has a similar attitude in identifying the front object or front vehicles with the conventional vehicles that we have here. You can see it follows the same car following model for the Vidman 74 actually. And the other parameters that it has, actually there is missing column here for the standard still distance. Standard still distance is 1.5, similar to other AVs, but for additive part of safety distance and for multiple part of safety distance, we have lower values or higher values, depends because it's calibration. Otherwise, the default parameters is 2, but here we have 1.5. If you compare these values with the other AVs that we have in the system, yeah, the multi-captive part of safety distance is similar to other AVs, but we have 1.5, like the cautious one for the safety distance, and for the standstill we have also 1.5. It is similar to the cautious one, but we don't have the emergency braking here for this AV, and we have a higher increase in acceleration. So it makes it in some cases a little bit aggressive because it has higher acceleration in comparison with the conventional vehicles or cars.
Awesome, thank you. The last question we have is, while optimization converge faster, the generic algorithm reaches a lower value of the objective function. So why would you come up with, you come up determining that particle swarm optimization algorithm is the best one?
Yes, that's a good question, because the iteration that we have here to have the faster result is kind of the constant error that we have here, or maybe close to the 0. So yeah, the genetic the actually wall is faster genetic second, and the PSO even is longer that one, and it's going to be after 45. But the iteration is not the issue. Yeah, we can wait for higher iteration. It's a kind of the higher number of the tests that we have, but the results of the objective function is important for us. That is going to be what's the result of the objective function. This is a deviation of the headway result, headway distribution, and by evaluating between the final results that we found for this distribution of the headway, we found that actually PSO has a better result, and we can rely on parameters of the driving behaviors based on the PSO.
Awesome. Thank you for that wonderful presentation.
No
I will now be presenting. I will now introduce.
Thank you.
Thank you. Thank you. I will now introduce our last presenter. His name is Parthiban, and he is from Jyoti Engineering College. Take it away.
Thank you, Brian. My screen is visible?
Yes.
Okay, and thank you. Today's my presentation is my master's degree thesis titled Pedestrian Flow and Capacity Analysis at the Railway Station. I'm the Parthiban, Jyoti Engineering College, Thrissur, and my project guide is Archana. She is an assistant professor, Department of Civil Engineering. Introduction. Here is the introduction part of the project. Is, as we know, the pedestrians are the important elements of the transportation system. Since every person trip begins and ends in the walking, the study area is chosen as main is Indian railway system. It's an mass transit system. It's run by the Indian government as a public transportation system, and it's the 4th largest railway network in the world by the route length, and covers an 8 billion passengers are traveling in the year. In the recent year, more number of passengers are traveling by the Indian Railway has been increased significantly, especially in the pilgrim season, because India is famous for the pilgrims, and which increases all the pedestrians and passengers are using for traveling purpose. They are using the railway systems, which increases the pedestrian movements capacity and risk congestions in the railway station. Even if arrival of 2 or more trains in the railway station is eventually led to the discomfort and the delay of the movements in the passengers. To resolve this problem by taking the recorded videographic footages in the railway station premise by using the simulation models, it's an easy process for the pedestrian networks to develop with the help of the PTV Vissim. And then the PTV Vissim, I'm following the guidelines of Indo HCM 2017 and NPFA. It's a National Fire Protection Association of 130 codings, and Indian Railway Work Manuals 2009. And then this is the Indian Railway. This image shows the mass transit system in Indian Railway. You can see the bottom left bottom image is an open entrance in the Indian Railway. Most of the stations having this type of the entrance only, so we cannot control the passengers in and around without if they are taking the tickets or not, and we cannot monitor. If we see in the another side of the right bottom of the image, it's an metro station. In India, there is a metro station and having an ticketing gate entrance. It's an this type of the systems wants to implement it in the mass transit system. For that, the simulation software plays a vital role. And then based on the literature review, I'm taking that the project as then from, and based on the some of the literature reviews, the parameters are taken for the evaluations. For this study, the literature were focused on the pedestrian flow characteristics on the stairways, FOB, and the platforms at the different locations of the railway station in and around India. And by concentrating on the pedestrian attributes on the basis of age, gender, and luggage carrying capacities, and based on the parameters of the pedestrian, I'm taking the flow, density, and the speed. And based on some of the literatures, the study area of the India, the existing facilities in the railway station, it's not satisfied by most of the pedestrians. And as we see in the literature reviews, not much work has been done for the entrance or the exist of the Indian railway system, especially for the Kerala state. For that, based on these literatures, I'm taking the guidelines of Indo HCM. Indo HCM is an highway capacity manual. It's recognized by the Transport Research Board (TRB) and then ASTRO and Federal Highway Association. Based on the Indian policies and the Indian work condition, we have framed the highway capacity manuals for the pedestrians. That is called an Indo HCM. And the objectives of my project study is to estimate the capacity of the passenger flow and to stimulate and forecast the pedestrian flow by using the PTV Vissim 11 software. And here is the methodology. Study area having the 2 railway stations, because the pilgrim seasons, especially in the Kerala, having the most demand passenger movements is at the Kottayam and the Chengalur railway station. And the data collection is collected by using the inventory survey and using the CCTV footages at the structures. And these, based on the CCTV footages, data is analyzed for the flow, speed, density, and the space of the pedestrian. And then capacity estimation is by using the Vissim based on the guidelines provided by the Indo HCM and the Indian Railway Work Manual and the NPFA. Based on that, pedestrian level of service has been found. Based on that, the conclusion has been made for the improvement of the future developments. And the data collections, this is the videographic surveys are recorded from the CCTV footages. Based on the recorded footages, the data is extracted as maximum flow, speed, density for the 2 railway stations and the structures of stairways and the entry and the exit. And then here is the to stimulate the vehicle or the pedestrian network. These are almost 11 softwares available in the transportation field market for that vehicle and the pedestrians. And Based on some of the infrastructures of the software and the general criteria of the softwares as the previous slides is evaluated by using the easy and effective handling of the vehicle and the pedestrian network, the simulation process. These are the criteria to take out the softwares for the simulation purpose. And based on that, comparative tables for the traffic stimulators or tabulator, in that the Vissim satisfies the most of the criteria, especially in the easy of codings and more flexible with the softwares using. And if you see in the students version, means the pedestrian and public transport vehicles and the emergency vehicles are easily simulated. And the Vissim is using the wireless sensor. It's an efficient and cheaper one to do for the simulation purpose. And Vissim is also supports by the GIS. And finally, by considering the infrastructure of the software for the user flexibility and the easy accessing, and also in the future development, the PTV Vissim plays a major role, and it's an useful for the basic of the simulation process. And why I'm choosing the PTV Vissim as me in consideration, in starting the project was initiated by the vehicle and the pedestrian interaction near the railway station. For that, the PTV Vissim is helpful support to that pedestrian and the vehicle interactions. And due to the COVID pandemic, the city is locked down, so unable to collect some of the data of the vehicles. And after looking at the webinar by the Tobai Christ, possible of doing the pedestrian simulation in Vissim it's cleared about its presentation and its webinars. Within the Vissim, this work can also be used to stimulate both pure pedestrian flow and the pedestrian interaction with the vehicles. So I am adopting the PTV Vissim 11 academic version. Based on that, the simulation of the 2 railway stations are stimulated for the pedestrian movement using the Vissim software, with the input data of total volumes and average speed of the pedestrians. And that result shows that the difference between the field study and the simulation study is there is having a difference in that 14 to 12%, having the variation in the values of getting the result on the stairways and the entrance of the passageways respectively. And these are the results what I get from the simulation and the experimental field study for the stairways and the entry and the exit of speed and the density. And then by using the Vissim, the pedestrian level of service can be easily evaluated by using the color scheme option with the support of the attributes of density or the space, and the number of flow and the average of the speed of the pedestrians can easily visualized. And then I'm using the guideline of JJ Fernin and Indo HCM 2017, and these are the 2 guidelines I'm following used in the Vissim software. In the left of the images showing that the pedestrians flow parameters, and the bottom of the image is showing the pedestrian, the space and the density of that. In the right of the images are showing the pedestrian level of service C, A, B, C. Like whenever the time interval changes, the pedestrian colors based on the color theme it's changed. We can easily identify when the where the interval of the time the pedestrian flow is increasing or the density is increasing, like that. And then for that entire railway station, we can also stimulate that. The overall railway station, we can easily visualize the pedestrian level of service of the entrance or the exit. The PTV Vissim is a more using for the pedestrian level of service to make an visualized to know about the density of the passengers, where they are accommodated, and the movement of the passengers are using. And then this is the simulation process. Same as the pedestrian level of service is visualized how the level of service changing in the time interval. When the train arrives, the pedestrian movement in the structure can easily visualized of the level of service from A to B and the C. The The maximum level of service as attained from the study area is in level of service C. And then same as the in the Vissim, we can also simulate the fire emergency exit. For example, if the accident happens at the railway station, it's a prediction only. It can be easily visualized how the passengers are evacuated from the station entrance. And if the entrance of the passengers are not easily analyzed in the area of the measurements options by using the walkout count, and this is followed by the guidelines of NPFA 130. It's a National Fire Protection Association. It's an working in the US. They are providing the guidelines when the fire accident happens in the buildings. The passengers should evacuate from that place within a maximum of 4 minutes, and then they are recommending that the minimum width of the entrance or the exit is an 914 mm. And the existing entrance, as I get from the 2 railway stations, are 3 meters and 3 meters same. That passengers can evacuate for minutes and 600 persons. In an average, they are evacuating, and it can be easily analyzed by using this PTV software. And then conclusion is finally, by considering the infrastructure of the software for the user flexibility and the easy accessing, and also in the future development of the PTV Vissim, it's a more convenient for the transportation engineers or traffic engineers to adopt or to evaluate the present situations or traffic congestions like that. And by comparing that field of the study and the simulation study, having a variation in the values up to 14 to 12% on the stairways and the entrance of the passageway respectively. Why I'm getting these type values variation means I'm using the PTV Vissim. The PTV Vis walk is an having a more realistic in the pedestrian walking behavior. If I have a chance, that means I go for that PTV Vis walk, and the error can be also be reduced. And then based on the pedestrian level of service, by using the color scheme for the area and the ramp and the stairways with the attributes, at the interval, at the regular interval of the time, the pedestrian level of service is changing, and the structures of the entire railway station can be analyzed easily. And based on this analysis, we can also recommend that the railway station having when the train arrives, this type of the intervals of the train, the passenger can accommodate in the ratio of more than 50%, like that. We can also be recommended for this purpose. The pedestrian level of service is more useful for that. If fire accident, in the fire emergency, the accident happens at the railway station, it's a prediction only. We can simulate that. We cannot after the fire accident, the number of passengers can evacuated from that structure, we cannot be imaginated. For that, the PTV Vissim is more useful for that prediction, how the fire accident happens, and the how many numbers of passengers or pedestrians can evacuate from the structure with that minimum of entrance or exit width can be easily simulated. And my gratitude to my project guide and also my college senior. He is one of the main part for doing this Vissim software, because he is working in the transport modeler and the new mobility solution in the PTV group Dubai. And I am also deepest thanks to the Elizabeth, because he is giving the every process for that student stock, and Malino and the Banton and the PTV Groups America, and especially for the PTV Vissim webinar series in the YouTube. It's a great helpful for the learner beginners to know about the Vissim software and how to work on it. It's a great support given by the Vissim group. And thank you. Have any questions?
Thank you, Parthiban. That was an amazing presentation. We do have some questions. Do you think that the social force model, the one that PTV VisWalk is based on, would reflect better than level of service?
Yes, if based on the social force model only, we can simulate the pedestrian movements in the Vissim or the Viswalk. It's an plays a major role because it's a social distance between one person and the another person. Yeah, it's an important one. Based on that only, I created a simulation.
Awesome. Which variables did you use for calibration?
And the calibration I used is an TAU, and the image is, the slide is showing. This is my calibration IDs
Yes.
used in that. TAU is 0.1, and the social force is 2.720, and the B social force is 0.2. Lambda is 0.76, and these are the parameters I get it from that PTV series only, web series only. That Mr. Toibo is thought that these are the parameters for the social force models. Based on that, I simulated.
Awesome, thank you. Another question we have, how many random seeds did you use?
It's an random seeds I used for that 42, 40, 41, 42.